Assalamu alaikum, dear student. I hope you are fine and doing well. Today, our class is about some basic which will be required in public key cryptography. In last class, we have discussed integer arithmetics, and in this class is also a continuation of our previous class. Today, our topic is modular arithmetics. In modular arithmetics, we are fundamentally basically uh, divide our set, which is set of integer, into a classes and call it modulo classes, or sometimes we call it as a clock arithmetics. Uh, Fundamentally, we have map our real line. I mean to say numbers that is placed on real line, that is number of element of set of integer if you have plotted on some line. So what does modular class means? Modular class means we have to bend this real or you can say the line in which we have placed our set of integer element, that all these lines will be number of element will be mapped on circle. In that case, or sometimes you call it as a uh, integer or clock arithmetics. So, dear student, we will talk about some modular arithmetics, and then we will talk about primarily about the concept of what you call it. Okay, primarily we will talk about some characteristics of modular arithmetics that which will be quite helpful for us in, in what you call in public key cryptography. So let me do it. So first, our objective is to emphasize the importance of modular arithmetics and the modular operator, and because as I told you in my first slide, it play a quite important role in cryptography. So modular residual matrices is also discussed because when you have extend your knowledge of public key cryptography over some non-commutative structures, like if you extend RSA, Schmidt, or other crypto system over a set of matrices. So there you need instead of number modular system of that is based on set and if it based on matrices. So here we haven't need the general sort of matrices. Here we need residue matrices, because residue classes in residue classes it is quite easy to calculate or to map some number set of integer to some set of plain text, like from set of letters to some set of modulo classes. So generally there are basically 26 letters in alpha in English, but how one can map these letters to some elements. So, dear student, the modular classes is quite helpful in that case when you have define the matrix from letter to set of some modular classes. So in that case, we have to utilize the modular arithmetics or residue matrices. So let us come up with first idea. Modular arithmetics is the basically the come up from division relationship. Like if you divide a by n, then a can be written as a equal to q time n plus r, where r is the remainder. Also, in whenever you divide some number to some element, then we are taking care about the remainder in residue modular arithmetics. So we will talk about these arithmetics. If you discuss the previous section, we have when A is divided by N, it two output Q and R. If you say that there is a two input, say A and N, you have corresponding two output, and we will always talk about remainder. So let us come up with some how the modulo operator will work. So if you can see over here, this is a set of integer, and you take any number a that which is divisible. If you divided it by n, then a can be written as a equal to q time n plus r. This is a one of the relation. This is q and r is non-negative integers. So it A can be written as a linear combination of Q uh, and R. So in that case, if you have performed modulo classes, say if you divide A by N, so mod it will give you just remainder. In that case, we will talk always about remainder. So in that case, if you can say the modulo class is the operator that give you the remainder after dividing any number with some other the positive number, say n. In that case, let us find some what does 27 mod 5 means. So if you divide 27 by 5, the result will be remainder will be 2. So we will talk about remainder. If you divide 36 by 12, the remainder will be 0. If you divide minus 18 by 14, the remainder will be minus 4. After adding modulus, R will be 10. What does it mean? If you can talk about 14, 14 divided by 14 remainder is 0, it means the 14 is the additive identity in modulo classes 14. You just add, if you have any remainder is negative, so you have to add 14 to which you are performing mod operation. You have just add 14. If you have remainder is negative, you have to add 14. In that case, if you add minus 4 plus 14, you will get remainder 10. Why it's happening? Because if you can say it is a modulo class 14, so in modulo class 14, the numbers start from 0 to 13. So there is no negative numbers. So if you add 14, so in that case the remainder is 10. So in 14 mod 14, it will r equal to 10 will be belonging from z 40, 14. So if you divide minus 7 by 10, the result is minus 7, because if you can say minus 7 if you add say it will be minus 7, because if this is greater than in absolutes, and if this is greater than 10, then you can divide, but this is less than. In that case you cannot. So if this is negative, so in negative there is no negative number in modulo 10, because whenever I say it is mod 10, it means z10. In z10 the modular class starts from 0 to 9, so you have to add plus 10 in minus 7. So if you can add it, then you will get remainder is 3. So as I told you in my first slide that we call it sometime as a clock arithmetics. So the set of modular classes in Zn is 0, 1, 2, 3 up to n minus 1. Whenever I talking about Z2, it means 0. There are two classes, 0 and 1. Whenever I talk about Z6, then the modular class is 0, 1, 2, 3 up to 5. And whenever I talk about 11, it means 0, 1, 2, 3 up to 10. So sometimes we call it clock arithmetics. If you can see in your daily life, your clock in your house. So if you can see, there are 24 hours in a day. So I mean, your clock is basically based on modulo 12. In modular 12, 12 is counted to 0. If you divide 12 by 12, the remainder will be 0. So this is 0. that start from 0, 1, 2, 3, 4, 5, 6, 11. Then 12 is, if you can place 12 or 0, it is congruent. So if you can say 1 and 1, then 13, if you divide 13 by 12, it is also 1. So 1 is congruent to 13 in modulo class 12. 2 is congruent to 14 in modulo class 12. 3 is, if you divide 15 by 12, the remainder will be 3. So 3 is congruent to 15 in modulo 12. So that is why you call it as a clock arithmetics. So if you can see, it's a quite famous clock. So generally there are 24 hours in a day. So this clock is very famous, that you utilize basically 24. Sometimes you call it as a 24-hour clock. If you can see over here, this is 0, 1, 2, 3 up to 23. So this clock basically tell you the whole about 24 hours. So in that case, if you can see, 12 is congruent to 0 and 13 is congruent to 12 from, and 23 is congruent to 11. If you divide 23 by 12, the remainder will be 11. So if you can place 13 or 11, these are congruent. These are not equal, these are congruent because they share one property, that 11 is if you divide 11 by 12, it is still remain 11. If you divide 23 by 11, the remainder is also same. So these are congruent. Congruent means to say any two dissimilar number, but they share one characteristics. Because 12 is congruent to 0, because if you divide 12 by 12, the remainder will be 0, and if you divide 0 by 12, the remainder is again 0. So in that case, these are common. Uh, Let me tell you what is congruent. I have also discussed it in my previous class, but I just refresh this because this will be utilized in our next slides. If a and b are two integer and n is any positive integer, then a is congruent to b mod n if n divides the difference of a and b. So we can write it a is congruent to b mod n, or sometimes a mod n is equal to b mod m. To show that two integers are congruent, who just use the congruent operator, this one. For example, 12, 2 is congruent to 12 under mod 10. If number is greater than 10, then you can say count remainder. So 2 is congruent to 12 because if you divided 12 by 10, the remainder is 2. So 2 is congruent to 12. 13, if you divided 13 by 10, the remainder will be 3. If you divided 23 by 10, the remainder is also 3. So 13 is congruent to 22. 3 is congruent to 8 because if you divide 8 by 5, the remainder will be 3. So 3 is congruent to 8 under mod 15. Similarly, this one. This is concept of congruent classes. You can see it's quite easy. So, dear student, who can call it as a these all these arithmetics related with the congruent classes, residue classes, modulo classes, or clock arithmetics. A residue class, a, or sometimes write it as with parentheses down in a lower strip, n, a set of integer congruent to mod n. If a and b are integer and n is positive, as I told you in last class. So in that case, if you can look over here, 1, 6, 11, 6, 21. These are one class. Where, because under mod 5, because it's because all these element, if you can see over here, these are all the element of set of integers, um, set of integers. If you can see over here, this one, these are all the element of set of integers. So if you can look over here, this one is not greater than 5, so 1 is remain 1. 6, if you divide 6 by 5, the remainder is 1. If you divide 11 by 5, the remainder is 1. If you divide 16 uh, by 5, the remainder is 1. If you divide 21 by 5, the remainder is 1. So it is congruent to 1. These are all those elements. If you divided it by 5, the remainder is 0. These are all those number from set of integer. If you divided it by 5, the remainder is 4. If we divide all these number with 5, the remainder is 3. If we divide all these number with 5, the remainder will be 2. So in that case, 0 class under mod 5 is all those elements which are multiple of 5. 1 class, I mean to say all those elements, if you divided it by 5 from set of integer, whose remainder is 1. 2 class, all those number if we divided by 5 in set of integer, whose remainder is 2. 3 class 3, modulo class 3 in modulo 5. If we divided all those element of set of integer, if we divided it by 5, the remainder is 3. All these are fall in the category of class 3 modulo 5. This is modulo class 4 under modulo 5. These consist of all those element of set of integer. If you divided it by 4, the remainder is, if you divided it by 5, the remainder is 4. So these are all classes. These are not just one element. I just place in this circle just positive elements. So you can place negative elements. In my next slide, if you can look over here, this is my next slide. If you can look over here under mod 5, what does I means? If you can look over here, this is my set of integer. These are my set of if I can divide the whole set of integer like this one into a 5 classes. This is my 0 class, 0 class. This is my 1 class from this to this. This is my second class. This is my third. This is my fourth class. So 0 class under mod 5, I mean to say from 0 plus all those numbers which are divisible by 5. In set of integer, there are positive as well as negative numbers. So I place is over here. 0, all those element which positive element, if I divided it by 5, will be placed over here. All these elements which are element of set of integer, if you divided it by 5, its remainder is also 0. So these are all negative. So similarly for under mod 4, uh, fourth class, third class, second class, and one class. If you can look over here, when I talk about 0 class, it is not just one element. These are number of element in one class, 0 class. If I can talk about one class, there are number of element that consists of in modulo class 1 under mod 5. So I just say this real line which is on which there is a element from set of integer will be mapped on this circle, and this is, you know what, 0 class, 1 class, second class. All these classes not just one number. It consists, every class consists of uh, infinite many elements of set of integer. So dear student, if you can look over here, as I told you, our daily routine life, the clock is basically the based on under modulo 12 operation. Here you can see over here. The 0 means 12 and 1 means all those elements, one from it start from 0 to 11, then 12 means 0. If you can place 0 to 11, it is also meaning the same thing. And if you can place some 13, 14, 15 up to 23 and then 24, these are also same because 1 is congruent to 13, 2 is congruent to 14, 3 is congruent to 15. Because if you divide 15 by 3, it is remains same. So in that case, this clock is designed the design of clock is based on modulo 12. So these are some binary operation how if you can take two element and operate some binary operation and mod it, then you will get set of modulo classes like this one. These are very simple example. You can go through from this example. Similarly, this one. This is very good example that basically give you the property of which is very helping while you are discussing high power of modular classes like 10 power n mod x can also be calculated 10 mod x as a whole power n. If you want to calculate it 10 mod 7 is 3, then it is same as if you can calculate uh, mod of 10, uh, 10 mod 7 to the power n. In that case, this will be a 3 power n mod 7. So this is quite easy. And if you look over here, so this property is quite good while you discussing higher power in modular classes. Dear student, prime numbers are quite important in cryptography, mainly that these give you the idea of prime factorization, and there are basically three types of problem in public key cryptography. One is integer factorization, and second one is discrete log base, and third one is ellipticals. So integer factorization is primarily based upon the primes and unique factorization of any composite number into a finite prime numbers. So prime is what? A positive integer p greater than 1 is called prime if and only if the positive factor of p are 1 or itself p. So in that case, the positive integer that is greater than 1 and not prime is called composite. Like fundamental theorem of arithmetics, that is any positive integer can be written as a product of prime or can be written as a prime factor. This is a fundamental theorem of arithmetics, which is quite important in all those crypto systems which are based on integer factorization. So RSA is fundamentally based upon integer factorization, and I must say in a generic way that it is based on fundamental theorem of arithmetics. Example. So if you can look over here, this is composite number. This can be written as a product of prime, that is 3 into 5. 48 is also composite. This can also be written as a product of prime or prime power into product, prime power of prime into prime. Or you can say 17, this is a prime, so it has only one factor, which is 1 or 17 itself. So 100 can be written as also product of prime or power of primes, like this one. So if you can see this one, like this one. So if dear student, if n is a composite integer, then n has a prime divisor less than or equal to under root n. It is easy to see if n is composite integer, it must have two divisors p1 and p2 such that P1 and P2 can be written as a product of this composite number. If I must say these are some characteristics you have to have sorted out by yourself, like this one. Uh, P1, P2 cannot both be greater than under root n because then P into P would be greater than n. If the smaller number of P1 and P2 is not a prime itself, then it can be broken into prime factor that are smaller than itself but greater than or equal to 2. These are some facts you have to keep this in your mind, so it will be quite helpful. So GCD, greatest common divisor, let A and B be the two integer, not both zero. Largest integer D such that D divides A and D divides B is called the greatest common divisor, GCD of A and B. The greatest common divisor of A and B is denoted by GCD of A and B. So if you can look over here, the GCD of 48 and 72 is, if you can divide it, the positive common divisor of 48 and 78 are these one. So the greatest of all these in both is 24. So GCD of 48 and 72 is 24. So similarly, if you can look over here, the 19 is prime and 72 is some composite number. So in that case, GCD of 19 and 72 is 1. In that case, we can say these are relatively prime to each other. Uh, Let us introduce some, say this one, like if you have this unique using prime factorization. So in that case, let me using prime factorization. I means to say if you A is any composite number, it can be written as a power of prime P1 to the power A1, P2 to the power A2, then Pn to the power An. B can be written also the power of primes. So in that case, where P1, P2, P3 are less than P1 is less than P2 and P2 is less than up to so on Pn. And similarly, A and B are belongs from some natural number for I greater than 1 and but less than n. In that case, the GCD of A and B is P1 minimum of A and B, P2 minimum of A2 and B2, so on. Pn minimum of An and Bn. If you can look over here the example, if A is 60 and it can be written as a power of prime like 2 to the power 2, 3 to the power 1, 5 to the power 1, 54 which can be written at 2 power 1, 3 power 3, 5 power 0. In that case, if you can look over here, dear student, if you can look over here, the uh, 2 the power minimum of these power. The minimum of 2 and 1 is 1, so I put it over here. 3 to the power minimum of 3, 1 and 3. The minimum of 1 and 3 is 1. So 5 to the power minimum of 1 and 0, this is 0. In that case, if you can multiply it, you will get the GCD of A and B, which is 6. Relatively prime. Two numbers, integer A and B, are relatively prime if their GCD is 1. In that case, we can say these are what you call the inverse of each other. They are relative because their GCD is 1. They are also 1 because GCD is 1, so they are relatively prime. In that case, the GCD is not 1 because the greatest divisor of both 37 and 28 is 7. In that case, 35 and 28 are not relatively prime. Pairwise prime is the element in which GCD of AI and AJ is 1. In that case, if you can look over here, uh, these are pairwise relative. If you can look over here, if you can look over here, uh, um, are these are because 15 and 17 are relatively prime, but 15 and 27 is not relatively prime. So in that case, these are not pairwise relatively prime, because pairwise relatively prime means to say each and every element, the GCD of each and every one with each other must be one. But in that case, these are not relatively prime. So if you can say 15, 17 are relatively prime, so we can say because in that case, yes, in that case, if you can look over here, I just put 28. So GCD of 15 and 17 is 1. GCD of 15 and 28 is 1. So GCD of 17 and 28 is also 1. So in that case, we can say these are relatively prime. Least common multiple. The least common multiple of a positive integer a and b is the smallest positive integer that is divisible by both a and b, and it is denoted by LCM of a and b. If you can look over here, the LCM of 3 and 7 is 21, and LCM of 4 and 6 is 12, and LCM of 5 and 10 is using prime factorization. If you can say any integer a can be written as a power of prime, and b is also can be written as a power of prime. In that case, LCM is the basically the product of p1 max of a1 and ab, p2 max of the power of this p2 is max of a2 and b2, which is power of this element and the power of this second element of b. So similarly, p and a to the power max of a and b, and in that case, if you can multiply all these, so we'll get the LCM of a and b. This is one of the example. So here you can see I just collect max of power between these two. The max of 1 and 2 is 2, so max of 1 and 3 is 3, max of 1 and 0 is 1. But in case of GCD, you get the minimum of this power. So the LCM is always greater than GCD. Yes, student, if you can see over here, the GCD of this is like I just collect the minimum of these to the power. The minimum from here to here is 21. So minimum from 3 to the power 1 or 3 to the power 3 is 3 to the power 1. So minimum of from 5 1 to 5 power 0 is this. In that case, GCD is 6. So if we can say LCM, in that case, I can get from these two elements the uh, maximum power element. This is 2 power 2. So again, so one theorem that multiplication of AB is equivalent to multiplication of GCD and LCM. Representation of integer, like how you can change the base of one element, and how you can change from decimal to binary and binary to decimal. This is the integer representation of any integer in some other form. So if you can say let b be positive integer greater than 1, then if n is a positive integer, then it can be expressed as uniquely in the following form, like this one. So where k is non-negative integer and a and b up to ak are the non-negative integer less than b, and ak should not be 0. In that case, if I can talk about base 10. I mean to say in decimal. I can say base 2. So in that case, if you can look over here, so 850, 850, 859 can be written as, because there are three elements. So its the product will be start k will be start from uh, 2, and it will be decrease, and then you will 10 power 0. So 10 to the power 2, 10 to the power 1, and 10 to the power 0. Then you can multiply just these number with 8 with this one, 5 with this one, and 9 with last one. In that case, this is the one of the representation of 859 as a base in base 10. If I can say a binary expansion, in that case, how one can represent this binary with the decimal in base 10. So in that case, if you can look over there, the coefficient of because there are 1, 2, 3, 4, 5 elements, so your k will be start from 4. So 1 to the 1 into 2 power 4 plus 1 into 2 power 2 plus because 2 power 3 is missing, because if we can multiply 2 power 3 with 0, then it will be 0. So 2 power 2 plus 1 into 2 power 1, then plus 0 into 2 power 0. So I just not write the all those elements which is multiplied by 0, because the resultant is already 0. If you can add all these, you will get 22, which is a decimal, or in decimal, I mean to say these are all elements in base 10. Similarly, we can perform hexadecimal expansion. In similar fashion, dear student, you can perform all these calculation. And this slide number 13 is left as an exercise. Similarly, this is also same steps as we have solved in our previous examples. So this example is left as an exercise. So inverses, there are basically in modular classes, dear student, there are some additive inverse and as well as multiplicative inverse. In additive inverse, two elements are additive inverse of each other if this property is all. If you can add them, these are congruent to 0 mod n. In that case, we can say these are additive, and A and B are additive inverse of each other. So in case of multiplicative inverse, if you multiply A and B and this is congruent to 1 mod n, in that case A and B are multiplicative inverse of each other. Like here, if you can look over here, the additive inverse pair in the 10 is, if you multiply 0 plus 0, this is congruent to 0 under mod 10. If you add 1 plus 0, you will get 10. If you divide 10 by 10, you will get 0. So 1 is the additive inverse of 9. Similarly, 2 is the additive inverse of 8, and 3 is the additive inverse of 7. In multiplicative system, A and B are multiplicative inverse of each other if A is multiplied by B and it is congruent to 1 mod n. So if you can look over here, I want to find the whether the inverse of it exists in Z10 multiplicative. So I have just one quite good what I can say technique of calculating the GCD of 8 with 10. If its GCD is 1, in that case we can calculate inverse. If its GCD is not 1, in that case it has no inverse Z10. If you calculate GCD of 10 with 8, it is GCD is 2, so it is not 1. In that case, we can say it has no inverse multiplicative inverse Z10. And how to calculate the inverses in Z10? So sometimes we call them as a unit element. We calculate in Z10, we have basically uh, 10 elements that start from 0 to up to 9. So all those elements having GCD with 10 is 1, and we can calculate their inverses. So 1, 3, 7, 1, 3, 7, 9, the GCD of 1, 3, 7, and 9 are 1 with 10, so it has multiplicative inverses. So in that case, dear student, if you can look over here, the pairs of inverses, multiplicative inverses in 11. 1 is inverse of 1, 2 is inverse of 6, because if you can multiply 2 with 6, you will get 12, and under mod 11, this is 1. So 12, 2 into 6 is congruent to 1 mod 11. If you can multiply 3 with 4, what you will get? You will get 3 into 4 is congruent to 12 under mod 11, and if you divided it by 11, the remainder is 1. So 3 into 4 is congruent to 1 mod 11. In similar fashion, you will get all the inverse like this. This is extended Euclidean algorithm. So we have already discussed this in our previous class. I left it as an exercise for you people. You have to uh, take it as a homework, and for this, dear student, through this is one of the application of Euclidean extended Euclidean algorithm. How you can use it to find out the inverse, multiplicative inverse, and modulo classes. These are some of the examples which we have discussed in our previous class. So a unit element in set of integer modulo. So unit element can be written as all those elements whose GCD with n is 1 from Zn except 0. Z26 I means is 0, 1, 2, 3 up to 25. Z2 0 means excluding 0, because the 0 does not has multiplicative inverse. So unit element of Z26 are 1, 3, 5. All those elements in this uh, said was GCD with 26 is 1. So I place it over here. So these are basically our 12 elements in Z26 was inverse is possible. And these are the what you call the multiplicative inverse of 1 is 1. Multiplicative inverse of 3 with 3 is 9, and multiplicative inverse of 5 is 11. And similar way, multiplicative inverse of 25 is 25. So this is one of the Calais table, how you can add and multiply the Calais table. So if you just add it, this is 0 up to 9, and these are also element of Z27 from row wise, and this is column wise. So you just add so row wise and column wise, 0 with 0 0, 0 with 1 1, 0 with 2 is 2. So in that case, if you can see, there is no repetition in row and column wise. So under addition table of modulo 2, this form a group. So this is also a abelian group. So dear student, from here, if you can see, if you can eliminate this 0 first row and first column. So other than this, if you can look over here, so there is a repetition of 2 over here, and there is some zero divisor in that case, because there is no zero divisor in field. So this is not what you call the field, because in a field is always a group under multiplication to. In that case, we have just multiplied the 0 with 0, 0, 1 with 1 is 1. So multiplicative inverse of 1 is 1. So 3 multiplicative inverse of 3 is 7. Multiplicative inverse of 7 is 3. Also multiplicative inverse of 9 is 9. So if you can see over here, if you multiply 9 with 9, the resultant is 1 under mod 10. So if you can look over here, the inverse of 1 is 1, inverse of 3 is 7. So all those rows and column, it consists of 1 and corresponding. If you go from row and look over here, the 1 and this, you can look above. So this will be the inverse of that element. If you can look over here, the through 3, the element 1 unit is over here. So if you go above, in that case the 3 inverse of 3 in that case is 7, inverse of 7 is 1, and inverse of 9 is 9. So rest of the other element, like 2 has no 1 in the row, so 4 has no 1 unit element, identity element, multiplicative identity in this row, and similarly 6, 5 and 6 has no identity, that is 1 in this row. So these are not what you call the unit element in Z26. And all the element whose inverses are exist, these are, we can call it unit element. So if you can look over here, the Z26, sometimes you can write it over here. Z6 steric 1 and 5, these are unit element. Z in Z7, excluding 0, uh, 1, 2, 3 up to 6 has what you call the all these element has have basically are unit element. It means to say all these element inverses exist. So in Z10, if you can look 1, 3, 7, 9, if you can see over here 1, 3, then 7 and then 9. So the unit element of Z10 are 1379. Unit element, I mean to say, dear student, all those element whose inverses exist. So in Z10, this element, this set is basically the set of unit element. I mean to say all those element in these modulo classes whose multiplicative inverses exist. In cryptography, often we use to move sets ZP and ZP static, because these are quite important in Z13, 0 up to 12, and Z13 static 1, 2, 3 up to 12. So matrices. I just in cryptography we are deal with modular or residue matrices. So what does residue matrices means? All the matrices whose GCD with some modulo is 1. That are basically the residue matrices, or sometimes we call it not generally. Basically, we will use all these matrices having operation of modulo class, like this one. Cryptography uses modulo matrices, and matrices where all the element are in Zn set of modulo classes. A residue matrices have multiplicative inverse if the GCD of determinant of A with n is 1. If you can look over here, the determinant of these 4 by 4 matrices whose element are from Z26 is 21. So the uh, so if you can see the GC in 26, the inverse of 21 is 5. If you can go back in this, if you can look over here, the inverse of 5 under mod 26 is 21. So if you can go there, the determinant is of A is 21, the determinant of inverse is 5. If you calculate its inverse, the inverse of this will be 5. In that case, if you can look over here, the GCD of 21 with 26 is 1, and GCD of 5 with 26 is also 1. In that case, these sort of matrices are quite important while encrypting or decrypting your messages. If GCD of any determinant with n modulo class, our n is not 1, In that case, you can just encrypt your message, but you cannot decrypt your message in a unique way. So the homework, how many matrices of 2 by 2 we can construct our modulo 26? This is one of the my question. And how many matrices of n by n we construct our modulo m? Journal, this is the, this, if you answer this one, so you can quite in a handsome way you can answer this question. So thank you all, and please stay at home. May Allah bless you all. And I just end up with one of the famous quotation of Albert Einstein. Learn from yesterday, live for today, hope for tomorrow. The important thing is not to stop questioning. So keep trying to question regarding my lectures, and I'll be quite glad to listen your question. And please stay at home. May Allah bless you all. Thank you. Allah Hafiz. And these are some references. Allah Hafiz. Till then, Allah Hafiz.